Hey, how's it going? Okay, so this is going to be the first 211 lecture that we have online, unfortunately due to coronavirus. I hope everyone out there is taking care of themselves and that everyone's okay. We've had to convert to an online format. As everyone knows, of course, the school has been closed down to in-person meetings, so we're just going to kind of have to make do with what we have, and I promise you we'll all just get through this. Okay. So today we're going to go ahead and cover nodal analysis. Now, nodal analysis is kind of similar to what we did last time, which was mesh analysis, where nodal analysis takes where mesh analysis takes a voltage approach using Kirchhoff's voltage law. Nodal analysis will be taking a current approach. However, nodal analysis is similar to mesh in that they're both kind of a formulaic approach to solving these problems. So you run through a sequence of steps and you arrive at the correct answer. It's fairly foolproof. We just need to correctly apply the steps, derive a system of equations, and then solve that system of equations. So over here I've gone ahead and listed out the steps. So with nodal analysis, we're going to start off by labeling a reference node. In other words, what we're going to do is we're going to pick a point in our circuit and we're going to call it 0 volts. So for labeling the reference node, we're going to use the ground symbol. And we're just going to pick a point on our circuit, call that 0 volts. We'll then be assigning node voltages. So every point in your circuit that has a different voltage, we're going to be labeling it as V1, V2, V3, etc. Okay, once we have that, we'll apply KCL. So in other words, we're going to write some Kirchhoff current law equations for each non-reference node. That would be your V1, V2, V3, etc. And then we'll have a set of equations once we're done with step 3, and then we'll just have to solve that system of equations. Okay, so probably the best way to do this is just to start off with a problem. So let's go ahead and just give ourselves a practice problem to apply these steps to. And to make our first one kind of simple, we're going to stick to using current sources instead of voltage sources. So I'm going to start off with a 3 milliamp current source. $500 ohm resistor here. Another 500 ohm resistor up here. A 1K in the middle. $500 up there. $500 over here, and then we'll give ourselves one more current source. There we go. Okay. So 300 milliamps, 500 ohms, 500 ohms, 1K ohms, 500 ohms, 500 ohms, and 4 milliamps. Okay, and already you can kind of tell from this circuit that this would probably be quite tricky or difficult solving it using any of our previous rules and methods. But as you'll see, nodal analysis will actually make this quite easy to solve. So first up, remember our steps. Okay, step number 1. We need to go ahead and label this reference node. All that means is we're going to pick a point in this circuit and we're going to call it 0 volts. Now, you can actually make life a little easier by picking a spot that sort of makes sense, right? Now, when I look over here, I see that from this current source, I have current going this way, right? And same thing over here, 4 milliamps, current's going this way. So I'm going to pick a point in this circuit that actually kind of makes sense to call 0 volts. I wouldn't necessarily say that, this doesn't quite make sense to say that this is 0 volts or this is 0 volts up here. But over here, this looks like a good spot to assign our reference node. Okay, so I'll just label that as reference node. In other words, 0 volts. Cool. Okay, so that actually takes care of step number 1. Next up, we need to go ahead and assign node voltages. So everywhere in this circuit that you see a point that would have a different voltage, we're going to label that as V1, V2, V3, etc. So let's go ahead and kind of just look around this circuit right now. Over here, notice this is all a direct wire that's connected to our reference node that we already labeled as 0 volts. Same thing over here, over here, over here, over here. Everywhere along this wire has 0 volts. So I don't have to label anything here. However, look at this point over here. I'm going to go ahead and label this as V1. Now, again, I get a voltage drop across this 500 ohms. So here's another spot. I'll label this as V2. All right. And here's another spot. I'll label this as V3. Okay. So now I'm looking and I don't see any other spot. This is all right here. This is all V3. This is all V2. This is all V1. Anywhere connected with a wire to V1 is V1. I already have that labeled. And all of this is 0 volts. So I have every single voltage accounted for in this circuit. So now we get on to the next part. This is probably the harder part of applying this, which is going to be to apply KCL to each one of these non-reference nodes, right? So the non-reference nodes, we already have those listed, V1, V2, V3. So if you think about what we're trying to do, we're going to go ahead and write out a KCL expression for V1. And then we're going to solve that and arrive at an equation. We'll write out a KCL expression for V2, and then we'll solve out that equation. And we'll get another equation for V3. So let's go ahead and let's look at V1 over here. And we need to go ahead and start writing out those Kirchhoff current law equations. Okay, now to make this easier, I'm going to go ahead and just start drawing and assigning currents to every single current that's either entering or leaving V1. So over here, look at this wire that's going in or leaving V1. If you notice, I already have it listed. In other words, I have a constant current source of 3 milliamps that says I have current going into this node at 3 milliamps. So that's almost a given. So let's go ahead and let's write over here I have 3 milliamps entering V1. Okay? Now, we move on to these next ones. We have 2 more. We have this 500 ohms and this 500 ohms. And now I need to pick a current direction. I can either draw my current going up or I can draw my current going down. However, to make the expression a little easier to write, I'm going to always work off of the assumption that V1 is higher than my 0 volts down here. It's not a bad assumption. Now, keep in mind, I could draw it to go up. The equation would be solvable. I would get the correct answer, but I will have less negative signs in my expressions if I pick the direction to go down. So I'm just going to make the assumption V1 is higher than 0 volts, right? Current always goes from a higher voltage to a lower voltage. So I'm just going to say that my current is going down for this 500 ohms. Now, I don't know what the value is yet. I'm going to go ahead and just call it IA. Okay, now same thing for this 500 ohms. I need to pick a direction, say it goes to the right, say it goes to the left. It doesn't really matter. In this instance, I have V1 on this side, V2. I don't know which one is higher than the other, so I can't really, make an educated guess over here. So it doesn't really matter which direction I pick it to go. So I'm actually going to write this one such that it is leaving the V1 node. And I will call this IB. Okay. Sorry if that's a little small. Okay. So now I have all currents listed for this V1 node. So, great. Let's go ahead and let's write what this KCL expression is. So over here, I'll say we're working with node V1. And the KCL expression, well, look at what's going on here, right? The sum of all currents entering a node must equal the sum of all currents leaving that same node. Well, what are the currents entering it? It's 3 milliamps. And that should be equal to all the currents leaving that node. So the currents leaving that node is IA plus IB. Okay, so we're about halfway there to our first expression. However, we need to go ahead and rewrite IA and IB in terms of the resistances and the voltages that we have in this circuit. So, I'm going to go ahead and now write out what IA is equal to. Now, over here, notice what's my voltage drop across the 500 ohms. I should say our motivation is we're going to write what IA is, the current, in terms of voltages and resistances. So really all we're doing is using Ohm's law here. If we know the voltage drop across the 500 ohms and we know the resistance, which is 500 ohms, then we can express Ohm's law and just say that IA is equal to the voltage divided by the resistance. Well, because our reference node is here, we've already said that for the sake of solving this, this point in our circuit is 0 volts. So when I have V1 over here, my voltage drop across the 500 ohms is simply V1, right? It's already in reference to 0 volts. So my voltage drop across the 500 ohms is V1. And if I divide that by the resistance, 500 ohms, then I have my current. So I've already said what IA is. I already know what IA is, my current. It's V1 divided by 500. So that takes care of IA. Let's go ahead and write out the current IB for this 500 ohms over here. Now, what is IB going to be equal to? So notice here that I now have two voltages that are involved. I have a V1 and a V2. So my voltage drop across the 500 ohms is going to be the difference between V1 and V2, right? So I just need to take the difference between V1 and V2. Now, in order to do this correctly, I'm going to advise to pay attention to your polarity. Current always flows from a higher voltage, I'm denoting it with the positive sign, to a lower voltage, which I'm denoting with a minus sign. Okay, so regardless of how I picked this current, we're working off of the assumption that it goes from a higher voltage to a lower voltage. So now I can say plus V1 minus V2. See how I did that? Plus V1, looking at the polarity, minus V2. It's actually really similar to how we did KVL back in the day. Okay, so IB is going to be equal to the voltage drop divided by the resistance. Well, the voltage drop across the 500 ohms is positive V1 minus V2, all divided by 500. Okay, so that gets us our expression for IB. Okay, so now we have a KCL expression and we have our two currents defined. So now we can write out our first expression, which defines KCL for this first node. So I'm going to go ahead and do 3 milliamps equals IA, which is V1, divided by 500, plus IB, which is V1, minus V2, divided by 500. And right there I have my first expression. Okay, this is what we are looking for. Okay, so that takes care of our node V1. Okay, next up we need to go ahead and do node V2. Now for our node V2, again I need to pick some current directions so I can write out KCL. And again, it really doesn't matter which way I pick my currents. So let's just go ahead and look at this first one over here. Okay, this 500 ohms connected to V2. I could pick it to go to the right. Doesn't matter. I could pick it to go to the left. It doesn't matter. I'm actually going to pick it to go to the left. Okay, now again, I don't have a current, so I'm just going to go ahead and label this as IA. Now, keep in mind, I'm reusing this symbol IA. This IA is not the same as this IA. I'm just reusing IA, IB, and IC for the sake of the intermediary steps for arriving at my expression. If you notice over here, there is no IA involved over here or IB. So we're really just using this symbol for the sake of deriving our KCL expression. And notice that this IA, I said the current was going to the left, where this current was going to the right when we solved for our first one. So again, it doesn't matter. As long as I'm consistent and I write out my expressions, when I get to the very end where I solve the system of equations, it's not going to make any difference. Okay, now let me go ahead and list out what the current is going to be for this 1K Now for this 1K, I could pick my current to go up. Totally could. There's nothing wrong with that. I will have to, I would have to add in a minus sign to account for that. But I'm going to keep it easy, and I'm just going to say that my current goes down. And the reason I'm doing that is because I already had this voltage listed as a reference node at 0 volts, so I'm just going to say that the current goes from V2 to 0 volts, goes from a higher voltage to a lower voltage. I don't have a value for this, so I'll just leave it as IB. And then now I have my last one over here, IC. I could pick it to go to the right, I could pick it to go to the left. I'm actually going to pick it to go to the right so I can kind of show something here about how we write this KCL expression. If you notice, I've actually had it so that all of my currents are leaving the V2 node. Well, if all of my currents are leaving the V2 node, how do I go ahead and write out what KCL is? The sum of the currents leaving, the sum of the currents entering the node should equal the sum of the currents leaving that node. However, I wrote them that they're all leaving the node. So when we go ahead and write out KCL for our node V2, I'm actually going to say IA plus IB plus IC is equal to 0. Totally fine to do that, okay? So all the currents are leaving, therefore if I added them all up, they should equal 0, right? Conservation of charge, Kirchhoff's current law. Okay, now of course I need to go ahead and write out what each one of these is. So let's go ahead and let's define what IA is. What is IA equal to? Well, check it out. IA here is going from V2 to V1. This is why I switched colors here. Because now I said the current is going from V2 to V1. In other words, I've made the assumption that V2 is higher than V1. Okay, so actually a little hard to tell on the screen, but this is green and this is blue. The blue, positive and minus, is in reference to our V1. We already solved for that. So what I'm saying is that this no longer matters when we're writing this expression, okay? Since we're working on V2, we don't care about any of our previous work. Think about each one of these as a separate equation that we are trying to express. So my voltage drop across this 500 ohms is going to be plus V2 minus V1. See how I used the polarity? So I said IA, I picked the direction to go from V2 to V1, so I made the assumption that V2 was higher than V1. Whether that assumption is true or not doesn't matter. We'll get a correct expression anyways. So plus V2 minus V1, all of that divided by 500, right? So the voltage drop across the 500 divided by 500, that's just Ohm's law, gives us the current IA. So we got IA covered. Okay, now we need to go ahead and do IB. IB is pretty easy since we already said that this is 0 volts. I only have one voltage involved here, V2, so I can just say V2 divided by 1K is equal to IB. So V2 divided by 1K is equal to IB, and we're good. Okay, last up is going to be IC. I'll use the same little trick as I did earlier to make this easy, current always goes from a higher voltage to a lower voltage. So I'm assuming V2 is greater than V3. So now I can say the voltage drop across this 500 ohms is V2 minus V3. And it's divided by 500 ohms, so just Ohm's law here. Cool. Okay, so now I got my IA, IB, and IC for node V2. I'm just going to plug these back into my KCL expression, and I'll end up with another expression for KCL here. Okay, so let's do V2 minus V1 divided by 500 plus V2, this is IB that we're doing now, V2 divided by 1K, plus, now I got to go ahead and write IC, which is V2 minus V3 divided by 500, and all of this is equal to 0. Okay, so now I have an expression for node V1 and I have an expression for node V2. We got one left to do and we will have 3 equations, right? Since we had 3 unknown voltages, we're going to arrive at 3 equations with 3 unknown voltages. 3 equations with 3 unknown voltages will allow us to solve for those voltages. So I'm going to go ahead, switch colors here, jump over to red now, and we're going to go ahead and write out the equation for our node V3. Alright, I'm going to use another piece of paper over here so we can see both at the same time as we write out our expression for node V3. Okay, so again, we're going to have to pick currents. Well, check it out. This current source is 4 milliamps and the arrow is pointed upward. So that's almost a freebie right there. This is 4 milliamps going towards V3. Cool. Okay, check out this 500 ohms. Again, I'm working off of the assumption 0 volts here. V3 is going to be higher than 0 volts, so I'll just say this current goes down. Again, I could have picked it to go upwards, but it makes it a little easier because I can keep V3 to be positive. Okay, so this I will label as IB. And this one over here, our 500 ohms, I could pick it to go to the left, I could pick it to go to the right, it's not going to matter. I'm going to pick it to go to the left, and this will be IA, okay? And again, I could have labeled this as IB, labeled this as IA. It's not going to make any difference when I arrive at my KCL expression once I'm done finding it. Okay. So now let's go ahead and write out the expression for node V3. Over here, the sum of the currents entering must equal the sum of the currents leaving. I have 4 milliamps entering, and I have IA and IB leaving. No surprise, 4 milliamps should be equal to IA plus IB. Easy. Okay, now I need to go ahead and define what IA and IB is in terms of our voltages and our resistances. So over here, I'll go ahead and say what IA is. Same thing as before, IA, we picked it to go to the left. So we are working off the assumption V3 is larger than V2, right? Current always goes from a higher voltage to a lower voltage. So now it makes writing the voltage drop across the 500 ohms really easy. I can just say plus V3 minus V2. That's the voltage drop across the 500 ohms, so divide it by 500 ohms, just applying Ohm's law here, and we will get IA. We got to do the same thing for IB. IB, now again, I'm working off of the assumption V3 is larger than 0 volts because we said that IB is going down. So I can just say the voltage drop across this 500 ohms is simply V3. Divided by 500 ohms, just using Ohm's law there. And I now have my IB. So let's plug all of this back into our KCL expression, and we get 4 milliamps is equal to IA, which is V3 minus V2, divided by 500, plus IB, which is V3, divided by 500, and we got our third expression. Very cool. Okay, so once we're done, notice what we have here. We have V1, V1, V2, V2, V1, V2, V2, V3, V3, V2, V3. Okay, so we have three expressions, three equations, and we have three unknowns, V1, V2, and V3. Everything else is in terms of values that we already had. So all we have to do now is go on to our last step for nodal analysis. We just finished up step 3. All we got to do now is solve the system of equations. Now, you can go ahead and do this however you want for solving this system of 3 equations. I'm not going to do substitution. We would probably be here for at least half a day if I were to do this with substitution, writing all this out. I'm going to suggest that you go ahead and learn how to solve this using your calculator. If you do have a graphing calculator, and I'm pretty sure many scientific calculators can also do it, you can solve it as a matrix. Just look up, go to Google, and just Google solving a system of equations using matrix in calculator, or how to just solve it by hand using a matrix. It's pretty straightforward, and there are lots of tutorial videos on how to do that. So I'm going to skip doing that step because that's just going to take a lot of extra time here to show that. Once you've solved the 3 equations, we're going to end up with values for V1, V2, and V3. V1 is going to be equal to 4 over 3 volts. V2 is going to be equal to 7 divided by 6 volts. And V3 is going to be equal to 19 divided by 12 volts. Okay, let's go ahead and we're going to rewrite our original circuit. We're going to plug in these voltages, and I kind of want to show you what our result actually looks like over here. So let's start with V1. That's 4 divided by 3, or 1.33. 1.33, and it's repeating. I'll just take it out to do 2 decimal points. 1.33 volts. V2 is equal to 7 divided by 6, which is 1.16666, repeating. I'm just going to take it out to 2 decimal points again. And V3 is equal to 19 divided by 12, which is 1.58. volts. It's actually 1.5833333, repeating. I'll just again take it out to 2 decimal points. Okay, and now let's go ahead and redraw this circuit. All of the work, all of this, was just for the sake of getting these 3 values. Okay? Once we have these values, we don't care about all of that previous work. We don't need it anymore. It was just for us to get the answer. Okay, so again, I'm going to go ahead and write out the circuit. Constant current source, 3 milliamps. $4 milliamps for that one. $1K, 500, 500, 500, and 500. Okay, that was our original circuit, and we found our voltages, right? This first one was V1. We know that that is now 1.33 volts. We know that this one over here was V2. That was 1.16 volts. And we know that this one over here was V3 at 1.58 volts. This whole process of nodal analysis was just to get these 3 values. And should also say over here that this was 0 volts. Okay. Once we're here, we actually already know everything about this circuit. Once we have these voltages, so let's go ahead and let's answer a couple of questions here. If I want to know everything there is to know about a circuit, that means I want to know what the voltages at every point is. Well, I already have that. 0, 1.3, 1.16, and 1.58. But I also want to know my currents. Well, look at how I can arrive at my currents now. 0 volts here, 1.33. Current always goes from a higher voltage to a lower voltage. My current goes that way. Okay, what's the magnitude of that current? Well, 1.33 volts divided by 500. 1.33 divided by 500 gives me 2.66 milliamps. I'll just write it as 2.6 milliamps. Okay. What about this one over here? Again, current always goes from a higher voltage to a lower voltage. 1.33 is higher than 1.16. Current is actually going that way. And if we want to know the magnitude of this voltage, well, just take 1.33 and subtract from it 1.16, right? And if it helps, you can go ahead and again look at the polarity to help you out. Current always goes from a higher to a lower, plus 1.33 minus 1.16. So 1.33 minus 1.16 equals 0.17 volts. That's the voltage drop across the 500, right? So 0.17 volts divided by 500 gives us our current. .34 milliamps. Quite a small value there. Okay. Not much current going through that one. Okay, let's look at this 1K over here. 1.16 volts and 0 volts on the other side. So 1.16 divided by 1,000. 1.16 milliamps. Ooh, I forgot to draw the current arrow. I'll draw it right there. Again, this next one, current always goes from a higher voltage to a lower voltage. So over here, 1.58 is larger than 1.16. So the actual current's going that way. And if I want to figure out the voltage drop across this, I can go ahead and say, well, this side was higher than this side. 1.58 minus 1.16 is 0.42 volts. 0.42 volts divided by 500. 0.84 milliamps. All right, perfect. We're on to the last one over here. Okay, 1.58 on this side, 0 on this side, so our current's going down. And the voltage drop across this 500 ohm is 1.58. So we will just do 1.58 divided by 500 ohms, just Ohm's law here, 3.16 milliamps. Cool. And that is our final answer. Okay, so just a couple of things to sort of rehash. Remember, these were just intermediary steps in order to arrive at our equations. These currents, they're just tools. Our actual currents come from the final answer. So once we arrive and once we get these voltages, then we figure out what our actual current is doing. Okay, so not too bad of a process to step through. Like I said, as long as you just follow the process and correctly apply your currents and write out your expressions, you should get at the correct answer. Okay, so I'm going to go ahead and leave this off here. I know this is kind of a different format for all of us. I know this has been quite a bit for everyone. I really hope everyone is doing okay. Please take care of yourselves, take care of the people around you, take care of each other. I really wish and hope everyone's family is doing all right in this weird time. And please keep washing those hands, right? All right. So I will go ahead and email some updates and hopefully get this moving along. We're just going to bear through it, and we're just going to make it out of this all right and get through this class, all right? So again, please take care of yourselves, take care of everyone around you. All right. See See you guys later.